Okay, so now we're going to look at the relationship between viscosity, the vessel length, and the vessel diameter to pressure or blood pressure. So resistance can be calculated by this little equation here, 8N times L over pi r to the fourth, which sorry, I can't spell. Resistance. Okay. So this is where N is the viscosity of blood. L is the length of the vessel. And R is the radius of the vessel. So flow rate, or what we call volume flow rate, is denoted by Q. And Q, the flow rate, is basically the difference in pressure over the resistance. So if you put in this equation for R, and you do a little mathematical magic there, which I certainly don't expect you to do, you would get pi r to the fourth times delta P, or change in pressure, over 8NL. And that's volume flow rate. So basically how fast it's moving, right? So this equation here is called Poiselles equation. So this is just a guy that studied fluid dynamics and came up with this equation here. So if we look at this equation, and we're not going to calculate anything or anything like that. This just shows you what it is. But what in here can we even manipulate? So the viscosity of blood can be manipulated. The more, water you drink, the more hydrated you are, the less viscous your blood is, and the more dehydrated you are, the more viscous it is. But this isn't something that we would want to, or the body can really change on its own and change very quickly. Vessel length is the vessel length. It is what it is. It doesn't change. It's as long as it is. Not much you can do about that. It's pretty much a constant. The radius of the vessel, we know that can be changed through vasoconstriction, and vasodilation. Okay, so the body can adjust the radius of small arteries, basically arterioles, to meet the metabolic requirements of organs and tissues. So the body can adjust the radius of small arteries We're talking about arterioles. To meet the metabolic requirements of organs and tissues. And you can kind of see in this equation what a big effect the vessel radius, or even diameter, however we're going to call it, but in this case we're calling it the radius, how much effect it has. So r to the 4th power. Now, in this, we can also change delta P. We can change the pressure for volume flow rate. So if the body changed the pressure, what would happen? So if we're trying to get more blood somewhere and we're just changing pressure rather than the resistance, which is manipulating the size of the diameter. So the pressure itself, increasing pressure can cause vessel injury, broken vessels, and too little pressure can have an effect on perfusion. So the blood pressure itself can be changed through the vessel diameter being changed without affecting tissues and vessel integrity. So if we increase the radius, resistance is decreased. And when this happens, volume flow rate goes up. So the bigger the hole, the less the resistance, the more blood will flow and flow quickly. A decreased radius increases resistance, which decreases volume flow rate. And the more we vasoconstrict, the more resistance that blood encounters to go through the vessel, and the more turbulent the blood flow is, which makes the blood flow slower, sort of, in a way. It's kind of flowing faster, but it's not getting far, or it's not flowing a lot, because it's kind of flowing in circles, sort of, because it's has a way smaller area, and so that blood is being pulled back because of the resistance of the walls. So it's practically flowing in circles in a turbulent way. Okay, so that is Poisses' equation, and its relationship to the volume flow rate. So the next video, or the next thing we're going to do, is talk specifically about baroreceptors and where they are and how they work to have an effect on the pressure there.